See, terminal velocity refers to the the constant velocity that a body acquires while it is moving up or down in the field of gravity. If the body is heavier than the fluid it is traveling in, then the body would be moving down. And when it is moving down, it will acquire a velocity when the drag on the body is equal to the wet weight of the body. Wet weight of the body is the dry weight of the body minus the buoyancy force. So if we do this, then if we equate these two, we can find out the velocity. Now, while finding the drag, it is important we use the appropriate formula for the drag. Distinct cases. One is when the body is traveling at a very low Reynolds number, and the other when the body is traveling at a very high Reynolds number. When the body is traveling at a very low Reynolds number, that we call the Stokes limit, the Reynolds number is much less than 1. This happens if the viscosity is very large, like a body traveling in glycerine, or if the size of the velocity is very small. Microbes, dust particles in air, raindrops, small raindrops, very small raindrops in air travel at Reynolds number much less than 1. And if the body is traveling much less than 1, then the drag is given by the Stokes formula, which is 6 pi mu. It is linear in velocity. This is the formula that you studied in your high school. When in high school, the only case that is done in NCERT textbooks of physics is the case where the Reynolds number is very low. But all the applications they do in Reynolds number is very high. So all the solved examples and then those unsolved examples are those where the theory that they developed in that section in their 12th class book, 11th class book does not apply. So in fact, in that sense, this is a mistaken solution in the book. When the Reynolds number is very large, then the drag coefficient is typically independent of the Reynolds number that we have discussed when we were discussing approximations. And so large, when it's traveling at large velocity, or the viscosity is little, as when traveling in air or most light fluids such as alcohol, water, etc. In that case, then the drag is given by a constant drag coefficient times 1/2 rho v square times the frontal area of the body, the area that you see from the front. So for a sphere, the frontal area is the circle of diameter d, which area of pi d square by 4. Now, here, as you notice, the drag is like velocity square. For when the Reynolds number is moderate, then it is between about 1 to about 1,000. Are very simple formula would work. Does that is that satisfactory? Do you want something else?
Yes, sir. Satisfactory. Sir, what happened if body is a bubble, air bubble?
Body is a bubble. Okay, body is suppose we have uh, a bubble, let's say a very small bubble. There again, we will talk about two cases when a very small bubble, and we assume spherical, and normally the velocity would be very small, the Reynolds number would be small. So we can talk about the drag to be order of uh, that given by Stokes' law. Now, while studying Stokes' law, be sure to notice, and we had covered this in the lecture, that the drag is quite independent of the shape of the body. This drag formula has been derived for a spherical body, but experimentally it is shown that if the body is of any other shape, conical, multifaceted, solid, and for the same Reynolds number, the drag experience is about the same. So shape of the body does not matter in a very low Reynolds number case. And that is the assumption that we will use when the bubble is rising up. But as the bubble rises up in a fluid, the pressure acting on this reduces. Pressure acting on this reduces, that means the bubble expands. And if the bubble expands, that is, its diameter increases, then the buoyancy increases like d cubed, while the drag is increasing like d, the diameter. And this means that the body, even though we may consider this into be a quasi-steady flow, the body would be accelerating upwards. Say a bubble, you would have noticed, accelerates. If you've seen this in a glass, a bubble rising in a liquid is accelerating as it moves up. Satisfactory? Always?
Yes, sir. Yes, sir. Sir, in this case, I think the weight of the bubble
Something
is
is not clear,
neglected.
which I should repeat.
Sir, I want to say that in this case, the weight of the bubble is, I think, neglected. We can neglect.
Negligible. Negligible. You could very safely neglect the weight of the bubble if you're talking of a liquid. The density difference is the order of 1:1000. So the weight of the bubble can be neglected. You see the formula, if you remember the formula, it comes 1 minus
Okay.
rho of body divided by rho of fluid. So rho of body is very, very small. So it's rho of body divided by rho of fluid is of order 0. It's much less than 1. So it can be neglected very easily.
So, sir, bubble contains air in uh,
Yeah, yeah,
that's why we neglect
yeah.
them as compared
Because
to.
bubble contains air. Actually, in a bubble contains air or it contains vapor, but the pressure, but the total weight is very small. It's in the vapor state. So it's a negligible compared to the buoyancy force. So weight is negligible, buoyancy force. So it's a buoyancy force versus the drag. And the drag varies like D, while the buoyancy force is like varies like D cube. So it's accelerating as the D increases, it accelerates upward. But like you did in the problem, you are assuming a quasi-steady state. So at any given time, it is the bubble is traveling as the instantaneous terminal velocity. Okay,
Okay, sir.
so that what I'm saying is acceleration is much smaller, is quite small. So inertial forces are very small. The compared to the viscous forces. And so inertial forces at any given time can be neglected. Did it make sense?
Okay, sir.
Okay.
Thank you.
Any, anything else do you think I should cover?
Actually, I don't see your lectures, so I can't say anything about which topic is remain left. You can elaborate
You see, when some of
Bernoulli
the
equations.
more interesting topics that I cover are the low Reynolds number flow. In a typical textbook in fluid mechanics, the low Reynolds number flow are not covered. In fact, in my older edition of the book that you might have seen, I have not covered low Reynolds number flow in any details. But in the new edition that we are developing, it is fascinating to see the low Reynolds number flow. It's a whole new area. If you recall that with every set are sending a further reading and a set of video films that should be shown. There is a beautiful film on low Reynolds number flow. The reference is in the reading list that I've given, where there's a link to that film. It's you can see in the MIT website, National Committee for Fluid Mechanical Films at MIT. At that site, they have about 30 in 1960 fluid mechanics to uh, students. And I don't think better films have been made since then. Even
Till
in
now.
the last 50 years, no better film, 60 years, no better film has come out. And any person who wants to teach fluid mechanics, I'm not talking research, but anybody who wants to teach fluid mechanics must watch more than half of those films. A grand education in fluid mechanics. Are you aware of those films?
No, sir. I think the video is created by MITs, as you say.
Okay. With almost every week readings I have, in most of them, I have included some link to that site. I think let me explore that link if I can find this very quickly. Mm.
Okay, sir. I will see.
Sir, in case of creeping flow, can
This
you,
is,
sir,
just one
sir, in
second.
case,
The link for this is web.mit.edu. If you're noting down,
Okay, sir.
web.mit.edu
Web dot.
slash NCFMF, National Council of Fluid Mechanics from NCFMF.html. So this is a very good collection of films. There are some other films also by that person from Iowa. What is his name? I don't recall the name at the moment, but they're also very good. But they're nothing comparable to these films that I'm talking. You're saying something, maybe
sir, I was asking about in case of creeping flow, sir, regarding Stoke and Stoke paradox. Can you,
what is it? So I'm sorry, I'm not aware. I don't really recall. What is the Stokes paradox? What is Stokes paradox? Can you
Audio.
illuminate me? Can you please explain to me what is the Stokes paradox? Stokes law, I've heard. Stokes paradox, I'm not aware of. The creeping flow, low Reynolds number flow, low Reynolds number less than one. Are you talking about the reversibility of the flow? Is Stokes law deal with the reversibility? That low Reynolds number flow, very low Reynolds number flow,
Yes, sir. Yes, sir. That only. That only.
It's a beautiful experiment. If you take a flow and you move in one direction and then you apply force in the other direction, you will recover the original configuration as if it's a solid
That,
that stretched and came back to this.
sir, that is what I'm asking about. Can we find a similar solution for 2D flows that is flow past a circular cylinder that is in what I mean, Stokes paradox? That was I was. That only I was asking.
Reversibility, yes.
Yes.
No, it is. I don't know what solution. It is argument. Is argument when there is
Okay.
no inertia forces, then the time has no direction. When there are no inertia forces, the time has no direction. So
Okay.
whether T is T positive or negative, you change the sign of time, positive, negative, it goes back the same
Yes,
thing. And
sir.
that is why it is very difficult for very small animals to move by flapping their wings or flapping their arms, flapping their limbs. Because when they flap, they cannot fly, they cannot swim. If they flap their limbs, whatever force they get by moving their arms in one direction, and when they move it back, the force is reversed. So they keep on oscillating between those two, they cannot move forward. So then they have to change the motion. There is a very good reference for this, which is given in my book. If you send me a note, I'll send the reference to you. I think it is there also. It is. It's online. Pardon me. Pardon me.
Yes, sir. Yes, sir. I have seen one time Professor Sanghi has given us the link for low Reynolds number flows by
Yeah,
a fluid film by National Committee for Fluid Mechanics film, which you have told. Low Reynolds number flows by S.G. Taylor that I've seen. That I've
Taylor,
okay.
yeah, Taylor.
Yes.
Oh,
Yes.
Jeffrey Taylor, G.I. Taylor. Yeah.
Yes, sir. Yes.
Yeah. That is very good. But there is a beautiful book about swimming of small organisms. Life Under the Sea or something like that is a reference. I can send you that beautiful book. It's a thick book. You can download most of the book now from one of the other sites now. And it is something you'll enjoy.
Oh, yes. Yeah, okay.
Okay. संदीप काफी हो गया
ठीक है सर आपके वीडियो में सिर्फ आपका चेहरा आ रहा है सर थोड़ा सा वीडियो सेटिंग हो सकता है आप हेलो ऑडियो आ रही है सर आपके वीडियो में सिर्फ आपका चेहरा आ रहा है वीडियो में तो थोड़ा सा आगे पीछे होकर यदि हाफ बॉडी आ जाए तो ज्यादा अच्छा है सर
ऑलराइट ये ठीक है
हाँ ठीक है सर
ऑलराइट मेरा ख्याल था चेहरा ही काफी होना चाहिए
ठीक है सर
ऑलराइट थैंक यू वेरी मच देन शैल वी close this. Parvez and Abdullah, I must express my thanks to you for helping me out in this course.
Yes, sir.
Yeah.
Yes, sir.
And Sandeep ji, the hours you keep, the time you call me, it must be telling that you're working overtime in this job.
Yes, sir.
बहुत मेहनत करते हैं
Thank you.
बहुत काम Okay, fine then. Thank you very much.
Okay, sir. Thanks. Thanks a lot.
Thank you, sir. Thank you, sir. Thank you.
Bye bye. Sandeep, I think you close the meeting.
Bye bye, sir. Yes, sir. Yes, sir.